lecture today. Now, I see that that about half the students are logged in, maybe a little more, but so we are starting off because I don't think there is any point waiting longer for anybody to join in. So last week, I started off with the introduction to the operating system. I have covered problems with concerning the different subsystems. I also spoke a little bit about the different types of the operating systems and a little about the history of the operating systems. The important thing to remember for all the rest of the lectures is that the operating system is a part of software which is not really run by anything. It is a part of the system which is resident as soon as you start the system, and it is giving service to the applications which are run inside. Of course, there are some applications. Those applications are the other applications which are there are some system applications which a lot of people think of as the same as the operating system, but because that's what they see. There is also the desktop, the graphical user interface implemented by the desktop, which also is run, so is visible to the user, but most of the functionality of the operating system are the functions, the operating system functions, which are provided by the operating system. Those functions, as I have said, they are very similar to normal programming language functions. The only difference is that when you compile a program, you link the functions that the program uses into your image, which means your program contains all the functions you are jumping to. That's not the case with the operating system functions. They are part of the operating system, so they are all the time resident in the operating systems. I have discussed last week that there are different ways of calling them, either using special instructions or using just normal function calls. And I told you that originally Unix was using the second method. Nowadays, Linux is using special instructions, same as Windows, and that the reason is that it turned out to be a little bit faster. The processors which we are using nowadays are optimized to support the operating system through special processor instructions. In IBM 360, this instruction was called trap, and for that reason it's still called by that name. Sorry, just a question. Do you have any problems with receiving my lecture? Because a moment ago I had some message from the operating system that the connection is unstable. Or is everything good? Okay, so I think I will switch off the video because that might be causing the problems, and you don't need really to see me if you agree, of course. And you will just be seeing my slides and hearing me. Okay, So I hope this improves the connection in the internet, because of course I see myself quite well, but if there are delays, you might be seeing changes in slides delayed, and that's not very nice. Okay, so as I said, operating system calls are more or less the same as normal function calls, but they do a lot more when they are being processed, which causes them to require special treatment. These operating system calls, if you are using the special instructions, the trumps, or in Intel configuration, the instructions, they are called int instructions. In that case, you usually have a library, a normal library in between the system calls and the and your application. The only purpose of those system calls is to translate normal function invocation specific to a language or to a system you are using, and the specific way the functions are called in the operating system using the special instructions. So the speciality means that operating system instructions are often use another type of instruction, of processor instruction to invoke them. That's one thing that I have spoken about. Another thing is they may use a different way of passing arguments to the function. In normal in normal applications programming, whether you are using C, C++, Java, or whatever, the arguments are passed through the stack, which means that when your program wants to call a system function, of course, if you are programming in high-level language, you don't see it, but at lower level, the behavior is such that the instructions, first of all, read all the stack all the arguments of your call, a function call, onto the stack, and then they use the function call to call the function. Such a type of argument passing is called user area stack argument passing. If you are programming using assembler, which means a very low level of programming, then you have some other ways of passing arguments, and the one which is used quite often with the Intel processors is passing argument through registers. Each processor has a number of registers, which means general purpose hardware, which is part of the processor, which can keep some data from one instruction to the next instruction. So instead of keeping arguments in memory, and in memory normally that would be the stack, you can pull them from memory into registers, and when you are calling a function, it knows that in specific registers it has specific values, specific arguments. And this is the most common way of passing arguments when you have special instructions to the processor. Of course, if you are passing arguments through registers, then you are not compatible with between different processors, because different processors have different numbers, and different organizations of registers, which means that this is a very low level. But for the operating system functions, that's enough. So a lot of system functions are called using registers, but not by your program, by special libraries. So there is a library which behaves like any library. So if you compile your program, all the arguments are being put on the stack, and the call function then addresses stack values and in that way knows what are the values of the arguments passed into it. Okay, in case and that happens also with the libraries interfacing to system functions. Okay, so the library in that case then pulls the values from the stack and saves them into registers which are required for the specific system call. They call the system function using the special instruction, and they return the value to the function, library function, which then passes the value to the rest of the program. Okay, you might think that it's not very efficient because when you call a function, you stack values onto the stack, then you take them out of the stack into registers inside the function, and then you do the same thing on the return from the system function. But the point is that it is quicker than working the other way, at least in the Intel architecture. And the other way, as I have discussed it, is to treat system functions as normal function calls, but jumping into system memory. Okay, there is a third method of argument passing. If you think about the processors through which you pass arguments to function, you must realize that some system functions might require a lot of arguments, and then you may run out of available registers in the processor. For that reason, a very common way of passing arguments to system functions is to use control blocks. And a lot of system functions which are used in Linux, they actually use the control block. What is a control block? A control block is a piece of memory which can be stored either inside user memory or inside system memory, and you pass not the values inside the control block, but you pass on just the address of the control block. If the control block is in the user memory, then you can just put in any values you want to the control block, and then you pass the address of the control block to the processor. But this is not very secure because you can, if your application can do that, also viruses can do that, and then you end up with a lot of problems. So nowadays, a lot of control blocks, if this architecture is used, and in Linux, as I have said, some instructions use the control blocks. Then the control block is kept inside the system memory. That means the program cannot directly manipulate the control blocks. Your program can just pass the address of the control block, but all the manipulation is done by system functions. So when you need to set up, for example, 10 different arguments to a function, and of course there are not that many registers, so the architecture requires you to build a control block, then you will have a system function for creating the control block, and then you will have system functions for setting up the various arguments, and you just pass the identifier of the control block to the operating system, to functions, and not the real values. And that way you can pass on a lot of arguments. This is what is being done, for example, in case of file handling. Handling files require a lot of arguments which have to be prepared beforehand. So what happens in that case is that there is a function for opening and operating, for opening a file. During that operation, the control block associated with that file is filled in by the operating system, and the function just passes out the ID of the control block. In case of control blocks of files, that is, it passes the file handle, because that's how the identifier is called. And all the other functions, system functions, which operate on that file, they require you to pass on as one of the arguments the file handle. Okay. At the end, you need to tell the operating system to free the control block once you have done everything that you needed to do with the file, and you do that calling the close function in the operating system, passing it the file handle. At that time, the control block is freed. The memory is reused for something else, and the identifier, the handle, becomes you cannot use any longer because it's not identifying any control block. Okay, so those are the different ways to handle arguments. If you invoke a system function, there is also a problem how you pass information about what happened in the when you were handling. Some operating system functions return something which is called return status, which means that they pass out some value, usually it's an integer, as the result of operation, and those value has special meanings. For example, -1 means that something failed, 0 means that everything went okay, and so on. So this is one of the ways of informing the application that something went wrong when you were when the application was trying to do some operating system function. There is another way. All the operating system have interrupts, and one of the interrupts is the programming interrupt, which is called exception. Okay, so instead of passing values as output of a function of a system function, you can raise an exception, and in such cases you might write your program in a way that it catches the exception when you want to handle them. If you don't catch an exception and an exception is raised, then your program will terminate with a stack printout showing you where the when during processing what part of your application program the exception was raised in. Okay, so that's a very important information for the during development. So during development, actually exceptions occurring inside your application are a more convenient way of identifying what is happening, because the status word you need to read and then to do something on that. But of course, when the program is to be distributed to end users, then you don't want to have any exceptions passing out of the program. So all the exceptions have to be called and handled inside of your software. Okay, system calls use both methods of informing you if the operating system function was successful or not. And you must know in case of any operating system function, what is the interpretation of the status word, and also whether it can raise exceptions or not. And if it raises them for an end user program, you need to catch them somewhere in your software. As I have said, since nowadays a lot of the operating system functions are invoked at a very low level, you cannot do assembler programming directly in C++ or in other high-level languages. So nowadays, usually there are special libraries or programming APIs which hide the fact that you are calling a system function. Instead, you are just treating them as normal functions. Okay, another thing that I would like to cover concerning the operating system, since we understand that most of the operating system is as just system functions. The system functions called something which is called the system kernel. The kernel is resident in the software, all the time ready to perform services to our applications, so we don't need to load it. That's the difference from normal library functions, which are part of your software, so they need to be loaded into memory when you are starting to run the program. Once they are loaded in memory, you can efficiently jump to them, but that increase the time for loading the program. Whereas the operating system functions, they are loaded once, not when any program is being executed, but they are loaded when the operating system is starting, which means when your computer is starting. Okay, so they will be quicker. They will not affect the time needed to load the program, since the operating system is resident. Okay, so there are two ways of working with the operating systems. You need to have some method of invoking commands, of invoking the programs, the applications that you want to run. Okay, the traditional method, which is nowadays very rarely used, but it is used by the system administrators, is the command interpreter. Command interpreter means that when the system starts, on the console, you get an invitation that you can log in, you can print in commands, and you can run the commands. Okay. Also, in all the traditional operating systems, even in Windows, which is nowadays not, such a system, you can invoke the command line from system console or from terminal. Okay. Command inside terminal, there must be a program which is actually communicating with us. This program, in case it's configurable, because when you start the system or when you log in, you can tell the system what shell you need to use. But then on the command line, you are actually, when you are inputting commands, you are communicating with the shell. In case of Linux, you are communicated with the bash shell. In case of Unix, a very traditional distributions of Linux, you might be communicated with C shell or with burn shell directly. In case of DOS operating system, which preceded Windows, there was a shell program which was called command com. So now traditionally, when you are invoking a terminal, it is usually often called command com or just command, but that's nowadays tradition. It has very little to do with the shell. It's just a command. Okay, it is a type of shell, but it's not what we used to have in MS-DOS. It's a different type of program. Okay, but in all those cases, when you are working with the operating from the command line, you are actually interacting with the shell. So what does the shell do? First of all, it allows you command line editing. You must have noticed that when you are pressing some keys, they are treated as function keys. When you press backspace, you don't get a indeterminate character which would correspond to the key code of the backspace key. Instead, the command shell, when it gets the information that you have pressed backspace, it deletes the last key that you have written on the command line. So that's one of the simplest way of command line editing. If you are working with bash, you will see that there are ways to do something which is called command completion. So if you type a few first letters of a command and then press a tab key, you, instead of doing a tab that is a few spaces, of printing a few spaces, the shell will either print out all the rest of characters because it has already guessed what you were wanting to write at this point in your command line, or it might display a list of possible things to use, and you can just choose which one of them you want to type in. So it speeds up typing this completion. Also, there is something which is called command line history. That means that instead of typing a command, you can use the arrows up and down to look through the command history and choose commands which you were using previously. So all of this is called command line editing, and it is done by the shell. Since there are different shells, as I have said, the command line editing might be either more robust or might be just very simplistic. Always, when you press a key, the command shell echoes the letter that you have pressed and interprets keys which are not displayed. But how it interprets those keys, how many different functionalities are there, that depends on the shell you are working with. Bash shell is a very complex shell, so it has every possible solution for command line editing. So you have lots of different ways to use those function keys. Okay, so that's one of the functions of the command line interpreter. Another function of command line interpreter or shell is that it supports system scripting. That means instead, if you need to type out a number of different commands to achieve a task and you do it repeatedly, so instead of typing 5 commands every time you need to do that, you can make a text file. Inside the text file, include all the commands that you want to execute, and then just run the shell. For that, run the script. For that, you do not need any additional software because shell is providing system scripting, and all the different historically simpler or more complex shells are supporting system scripting, which means that you always have at hand a tool for doing that. Okay, so that's one of the two functions. And the third function of the command line interpreter is to run commands. Okay. Before I go into the commands, I would like to tell you about the alternative technique being used nowadays. That is the graphical user interface. Okay. So when you start your program, or rather when you start your laptop, or when you start a virtual machine, when the operating system starts, it can also, at the end of all the other processing, it can start a program which is called a graphical user interface. And in modern operating system, especially in Windows, this graphical user interface is part of the operating system. And the the most important thing about graphical user interface is that it handles something which is called Windows, and also something which is called a desktop. So when you see a desktop, that means that the graphical user interface was run, and it will allow your application to be run in Windows using window decorations, which can minimize windows, maximize windows. Okay, so some things are done by the graphical user interface directly with your application. You don't need to, when you are programming your application, you don't need to do anything more, because when you call open a window, you have all those decorations. Of course, you may overload the handling of the different decorations, but normally you don't do it. That's it. So this graphical user interface is very convenient for the end users. It's not so convenient for automation of administrative tasks, and for that reason, all the administrators are still using command interpreter. So that means shell programming, and also the graphical user interface can often not support all the possible functionalities of the operating systems, and also for that reason, often the users will run inside the graphical user interface a terminal, and inside that terminal work with the command line editing, because you can do a lot more that way, of course, if you have the knowledge for that. Okay, so what does the shell do? Most important thing is to run commands. And to understand commands, you need to understand one very important thing, that actually there are two types of commands. One are called internal commands, and the other type of commands are external commands. Internal commands are commands built into the shell. So if you invoke an internal command to perform that command, the software executes parts of the shell. What does it mean? It means that first of all, when you invoke an internal command, the shell is already loaded into memory. This is not all the time, because when external commands are being run, then the shell can be removed from the operating system. But when you invoke a command and it's an internal command, the shell will just jump into the function and realize it. So there will be no file with the program for internal commands. Okay, external commands are different. They are programs which are stored on disk inside executable files. And when you invoke an external command, then the program is first of all loaded. The shell at that time is removed from memory. Okay, then the command is executed, and when it ends, the command executes the system function. The program executes the system function exit, and at that time, the operating system knows that the command has ended, and it will restart the shell, and you can again invoke other commands, which means that external commands take more time to load and then to switch back to the shell, whereas the internal commands, if you have too many internal commands in the shell, they will cause delays when loading the shell, because all the code for internal commands must be loaded at that time. So for that reason, you don't have operating system shells which are based only on external commands, and because something it is very needs to be done efficiently, quickly, so for convenience of working, but all the rest is moved to external commands, and the list of external commands is open, because any program you compile, you install on your computer can be executed as an external command. There is nothing specific to external commands in comparison to normal programs. If you are running a program and executing a program from file, you are actually executing an external command. So there are internal, like ls, like cat, like make dir, and there are external, like find, like grep. Okay, you will be dealing with both of them. The whole idea with the operating system is that they are invoked by the same, very similarly, by writing. Sorry, no, I don't have this slide. Okay, so by writing a command and then command arguments, as you have already done in the during the laboratory. Okay, and you will be doing it in the future laboratory classes as well. So that means internal commands and external commands look very similar when you are invoking them. The only difference is that internal commands will never have a path. Okay, so there will be just the name of the command because there is no file containing the executable, whereas external commands always have a path, but of course, file name is also a file path. If you just write the file name, it means that look for the file inside your current directory or inside a number of directories. In case of external commands, that means files executed, it means that look for the command file in a number of directories where external commands should be stored. The list of those directories is different in different operating systems. In both Windows and in Linux, you can customize that using the path external variable, because the operating system, when the shell actually, not the operating system, when it tries to execute an external command, it looks at the path system variable, and that path value lists the directories in which to look for the commands, for the files containing the code. Okay, but there is one but. Okay, the whole point is that inside, in case of Windows, the path variable lists only some of the directories, because there are some directories which are always searched. The Windows directory, when Win32 directory, they are always searched, even if they are not listed in the path directory. Okay, there is a very special problem with this. Sometimes an external command has the same name as internal command. In that case, the internal command will be run if there is no path, and the external command will be run when there is a path. That is, if you specify a path, not just by giving the name, because in that case, if the name corresponds to internal command, the internal command will be executed, but you need to have a path. So if you know that if you, for example, create your own fine program or any program or any script which you call find, and you call it from the command line just by writing find, okay, this is not a good example because find is an external command. So no, the example will be different. If you call your file ls and you write ls something, or if there are arguments or not, then the internal command will always be run. If you want to run a program, your program, which you have compiled, or your script, if you have done that, then you will need to write ./ls or a different path where the file is stored. If you write just ls, it will not work correctly. Okay, so my advice is to avoid using file names which correspond to internal commands, or which you suspect that might correspond to internal commands, because then you will have problems. Okay, so a very important thing to when you are working with the operating system is is using scripts. As I have said, you will be working with a shell which is called the born again shell. So the name of the file of the command is BASH. It's a shorthand for the full name of this shell. And this shell was developed to be compatible with the most traditional of the Unix shell, which is the SH shell. So if you invoke a bash script using SH, it will run just as well, maybe with some surprises, but actually it will still run. But you may, and you might do it because the SH was the first shell, so all the other shells actually try to be compatible with the SH shell. Okay, Bash has lots of other enhancements. Some of them are necessary, are very convenient. Some of them are very difficult to use, and I don't see any reason why they were introduced, because there were traditional ways to do it which did not need those enhancements, but you have them, so you can use them. Okay, so one of the an important thing is that whenever you invoke a command, whether it's a script, because a script is invoked as an external command really, or they are commands inside the script, then each command is, on each command, some command line interpretation is invoked, and you should have some to understand, especially if you run into errors when you are writing scripts. You should be aware of what happens when a command is being executed. Okay, when you write out the command and you press enter, the command you start to execute the command. Before the shell loads the program or jumps to the internal command code, it first of all does command line interpretation. Okay, if you use braces, those braces have special meaning on the command line, so they will be reinterpreted. If you use the tilde sign, that is the wave sign, it has a special meaning. Okay, if you invoke values of variables like $, name of a variable, then that will be interpreted in the command line interpretation. If you use on the command line the star symbol, it will be replaced. So I haven't told you how they are being replaced, because you are doing that in the laboratory, but you must be aware that that is happening. So if you, for example, want to remove all the files in the current directory, you will write in Linux a command like rm and a star. What happens? Rm doesn't understand stars. It's the shell, the command line interpretation done by the shell, which will interpret the star. It will look in the current directory, list all your files and directories in that directory, and put it in the command line in place of the star. So the star will be replaced before your program is being run. If you don't want to do it, you can either precede the symbol, which has special meaning for command line interpretation, with a backslash, or you can include it inside single braces. The single braces will disappear, but the all which is inside that, all text inside the single braces will be interpreted as literal text. Okay, so that is the first thing that is being done. Okay, so once the command line is reinterpreted, the new text which appears is split word by word. Okay, inside the shell, you can define what is used for word splitting. Normally, it's any white characters like spaces, tabs, also some non-white white characters are used for splitting, but that is I will not be discussing, but all the white characters, they are interpreted as word splitting. So if you have the command and then 7 spaces and 1 argument, all the seven spaces will be interpreted as a single splitting character. So when the word, the command line is being split, all the words are put into separate strings. So you have the first string with the command name or path, if a path was there. Then you have the first argument in the second string, the second argument in the third string, and so on. If you, inside the script, if you say $1, it means word, the second word in your command line. Of course, the whole problem is that in between was command line interpretation. So what you think is the first word might not be really after command line interpretation. So you must remember about that. If you want to have spaces inside some argument, you need to use the you need to use the quotation marks to make them a single argument. Sorry, for literal translation, I have also made a mistake. Not braces. I meant also single quotation marks, not single braces. Sorry. So when the word splitting is performed, the first string is used as the first thing, as the command, and all the others are arguments. So that is also passed to a compiled program. If you remember C language programming, you will remember that you have an IRGV table being passed to your program, which is an argument to the main function in your program, and inside the 0 indexed element is a string with the path to the command which is being interpreted. Indexed 1 is the first argument, index 2 is the second argument, and so on. So similar to scripting, where you have $1, $2 as the separate words, $0 as the command also, but it's not necessary for you. Okay, so I have already mentioned the star character. In fact, star is just one of the different characters which are used for for something which is called file patterns. All of them you need to interpret. Sorry, there is no. Okay, so words you need to if you use a file pattern, then the file pattern is also interpret any file pattern, just like star and other is used the same way. That means the shell is interpreting the file pattern and substituting the file pattern with all the file paths that it found satisfying the file pattern, which means that you might write just one argument star, and in fact, you are invoking a command with, for example, 10 arguments in the command line, and you can access them using $1, $2, $3, and so on. Okay, so another very important part of Linux scripting is something which is called pipelining. Okay, so what is pipelining? Pipelining is a technique by which you use the input-output streams used in the command line. When you invoke a program, the program is always invoked with some streams open. One is the input stream, where the program reads input from. Another is an output stream where it outputs the results. Normally, the input stream is your keyboard, and the output is your terminal window. Okay, so when you run a program, you type in some. Okay, arguments are not input streams because that's the command, but when you invoke the program and your program starts reading something, you will see that you need to type on your keyboard the arguments, and then the program will input to the terminal the results. That pipelining is the same as the that is normal behavior of a program. But on the command line, using the arrow notation, that means the greater than and smaller than symbols on the keyboard, and stating some file names, you can redirect the streams. If you put in command smaller character and a file, then the arrow is pointing from the file to the command, which means that it's a command input. And that means that instead of reading text from your keyboard, your program will be reading text from that file. If you use the greater sign and a file name, you are redirecting the output, which means that all the output of your program, instead of being displayed on your terminal as lines on your terminal, will be sent to a file of the name that you give. Okay, so that is redirection of file input and file output streams. And if you run two programs in parallel, then you can state that the output of one program must be the input of the second program. So you do that by writing the vertical line symbols. A symbol, that's the symbol above the / on your keyboard. And you can write one command, bar, second command, bar, third command, and all the three commands will be invoked at the same time. The first command will have its output redirected to the input of the second command. So whatever the first command will output will become the input to the second command. Whatever the second command produces on the output, since again you have by the vertical line redirected it to the third file, so the output of the second command will be redirected to input of the third command, and only the output of the third command will be displayed on your screen. This is a very efficient way of using a number of commands to process a text string. One command will process something, the second will do something else to it, and the third something still else. So using pipelining, you can build a much more complex commands than using just single commands. Okay. As I have mentioned, I have actually discussed already a lot of that. The command line interpretation is done using by substitution by shell of different text. Double quotes, their only function, they don't do anything to what is inside the text. So whatever you write inside this, the double quotes will be passed, not unchanged. Okay, it can be passed, changed or unchanged to the. So if you have some other like dollar variable inside, it will be substituted as normal. Once every substitution is done, the only function of double quotes is that they treat all the resultant text as a single argument. So they affect the way that the command is split in two words. If you use single quotes, then it affects also similarly to double quotes. What is inside is treated as a single word, which means a single argument to the further command. But also special characters are treated literally. So if you write the dollar variable inside single quotes, what will be passed to the program, to the command as argument will be dollar variable and not the value of the variable. Okay. Quote expansion, there is also something which is called back quotes or backticks also is being used, the name. So it's the character on the keyboard below the tilde character, which means below the wave character. Okay, so the backwards means that what is inside the shell will interpret as a second command. So if you have a command back quote as another command, the command inside inside the will be executed by the shell. First of all, the output from that command will not be displayed on your command line, but instead of that, it will be put in as argument to the command inside which the backquotes were being used. So, for example, if you are using for a in \ls, then not backslash, backquotes, ls backquotes, that means that first of all, the shell will execute ls, find all the files listed by ls, put it on the command line, and then execute the for command. And the for command, as you already should know, some of you were already doing the exercises with them. Some will be doing today. So the for command iterates through all the words which are after in. So that means for a in ls will mean that it will iterate as many times as the words produced by ls, and that means as the number of files found by ls, and at first iteration, the a will have the value of the first word, then of the second word, and so on. This is quote expansion. As you see, there are different quote expansion. Another thing is variable substitution. If you have a variable name, that's a text. If you write the variable inside a script or on the command line without the preceding $, it will be just a text of that name. If you precede it with $, then it means that the command line will be reinterpreted. That means the variable will be substitute the text which you write $var will be substituted with the name of the variable, the name of with the value of the variable. If the variable is defined, and for example have 1, it would be the same as writing just 1. If a variable is not if a variable is not defined, that doesn't matter, that will not produce an error. Instead, any undefined variable has the value of empty string. So in place of $variable on the command line will be just empty string. So it will be just deleted from the command line. Okay, instead of writing $variable, it's better to write and brace variable and brace because in this case you know when the text the variable name ends. Okay, this is exactly the same, but if you wrote after $var, for example, x, then then the text $var x would mean that you would be looking for a variable var x, whereas if you write $braces var and x after braces, then you will be looking for variable var, substituting the value and appending to it the x. Okay. Variable substitution always precedes word splitting, which means that if you don't back quote or if you don't escape the text or don't include in single quotes, then you will never get text with dollars inside it, because that will always invoke variables. Okay, so when another thing is file patterns. I have already mentioned star file pattern. There is another thing, the question mark, which stands for any character, or you can use brackets for stating all the characters which can occur at a certain point. So if you, for example, write ls question mark, you will get the listing of all single character file names, because ls is listing file names. Actually, if you write instead of ls question mark, just echo question mark, you will get exactly the same result. And if you have in the file a directory, you will have more consistent, really, from to what you expect. Okay, so a single dollar question mark stands for one character. Double, if you write question mark, you are looking for two-word files, two-character files. If you have in the bracket the A, just that means that at this position. So if you, for example, have bracket A, bracket, and then a star, you are looking for all files starting with character A. You can have negation, and if you put something like this in square brackets, up arrow and F, then that means all at this position cannot be F, but anything else acceptable. So if you write something like this and star at the end, it means all files which do not start with name F. Okay, so that's command line interpretation. And that's more or less all that I wanted to tell you about that. We still have, I think, 10 minutes before I need to end. So we will start another set of slides. Unless you have any questions to this part of the introduction, because at this moment I have finished introduction to the operating system, and I will start off dealing with specific parts of the operating system. Okay, are there any questions? No? In that case, I will start with processes and threads. And actually, I will start off today with processes, because certainly I will not be speaking about threads. Okay, so I should start off to tell you what is a process. Okay, when you write a program, it's a text file. Actually, if you compile a program, you get an executable file. When you want to run the program, you get a process, because a process is connected with running a program. So when you start a program, you are actually running a process. It's in most cases, the two statements are exactly the same. I won't be able to tell you about that today, but I will be telling you next week about multi-thread programs or multi-process programs, really. And in that case, you will realize that that might not be always the case, that running a program and running a process or running a program or executing a process is not necessarily exactly the same. Okay, so if a process is the execution of a program, in case of a sequential program, that's not a problem. That's what really it is. So we need to identify a program which is running. Okay, the name of a program is not enough to identify a process for the operating system and also for the administrator, really. So what we need is a separate way of identifying a process as a program. Program is identified by the name of the file containing the table, whereas a process is identified by a number. Why is that necessary? Because the same program in different windows you can run at the same time, or different users might even run at the same time. So inside the computer, the program name does not identify an instance of its running. Instead of that, you need to use a separate method of identification, and the method used is called PID, which means process identifier. So each process is identified by a distinct PID. There cannot be two different processes running in the system with the same PID. Okay, so there is one thing more. Okay, most of the programs, most of the programs are running. Most of the processes are running a program, but there are also in the system some system processes which are not executing any file, any program. Okay, so they have no program file name identified with it, but they also have a process ID. Those processes are actually executed parts of the code in kernel. And for that reason, they are called system processes, and they have no corresponding files, of course. Another important thing is that if you are running multiple programs, all those programs are using some system resources. What is a system resource? Actually, obviously, the memory, the processor time, input, output, but also some more complicated resources can be considered. So when a process is running, it is using some resources, and you don't want other processes to use those resources. That is called mutual exclusion of resources. So so when you are considering processes, those processes the operating system allocates to them resources, allocates the processor for some processing time, allocates the memory where the program is being stored during execution, allocates maybe some other resources as well. Okay, so if you do not want multiple processes to share the same resources, they are allocated exclusively to the process, and that's called mutual exclusion. But it's not always necessary. If you want memory for storing a program, you need to allocate it exclusively to that process. If you want memory to keep some variables which you want to share with other processes, then you will allocate them in shared memory, and then the allocation is called shared. Since shared allocation is easier on resource consumption, it is always good to allocate resources to processes on the basis of shared allocation. But if you allocate shared resources, then you don't have operating system protecting your resources. Whereas when you allocate resources to a process from mutual exclusion, then the operating system is taking care that no other process get access to those resources, to that memory. Okay. Okay, so when you want to execute a program, you need to allow it to use some processor. Nowadays, most of the processors have multiple cores, or computers have also multiple processors installed on the system boards. So there is a certain number of processors which can execute programs completely in parallel. But obviously, the number of those cores or processes is limited. So because of that, if you want to have the operating system running on multiple processes, not limited just to the number of processors, then you have to switch the processes which are being run. Okay, so you give a processor not for exclusive use to a process, but you just give them for some time slice, and when the when it's time to when it is necessary to process some other to give those processors to some other processes, then one process will be stopped and the processing will be switched to another. Okay, the easiest to imagine this is if you have just a single processor, then just one process can be run really in parallel, but you can have multiple windows, multiple processes running having the appearance of running in parallel, but in fact running in different time slices. So one is running for some time, then another is running for some time, and so on. So to achieve that, you need process switching, which means you need a mechanism by which you will stop one process from executing and switch to another process, which will start executing in its place. So process switching is divided into two main approaches: non-preemptive and preemptive. In non-preemptive, the process switching is initiated by the process which is running, which has the processor. That process comes to a system function. Inside that system function, the operating system decides that it cannot proceed with running this process because some resources are lacking or some action that is required by some other process has not happened yet. So in those cases, the operating system inside the system function start the process switching, stops the function which was stop the process which was running, and switches to a different process. Okay. In case of preemptive process switching, the switching may also be preemptive process switching does not eliminate switches caused by system functions not being able to proceed. But even if the process is not executing a system function, but instead that a timer decides that the process is running for long enough, the timer will generate an exception an interrupt, and then the operating system handling that interrupt will stop the process and start a different process. And this situation is called preemptive process switching. And as I have said, some operating systems does not have preemptive process switching, but then if a process does not execute a function which initiates process switching, that and then it can keep the processor indefinitely. And more usually nowadays that a process can be either switched by running out of the time slice that is being initiated, or else it can be initiated by the system function which blocks the current process. So the best situation is in multiprocessing when you have preemptive switching, because preemptive process switching allows you to work interactively by many different users with many different processes. Okay, and the response times are then ensured, that their reaction times are ensured. But preemptive switching is always consumes times, because you have to stop one process, initiate the other. In case of non-preemptive switching, you have also to stop one process and run another, but this is done in the time in which your current process could not run because it would need to wait for something. So in case of non-preemptive switching, you do not lose time for switching, because the switching just decreases the amount of time saved because you have switched from one process to another. Okay, so you have two types of process switching, and the rest I will be talking about next week. And for now, I think I need to end the lecture, and I don't have time for questions. Sorry for that. So thank you very much for attending the lecture. And in a few minutes, I will be starting with one of the group, the laboratory. So for now, it's bye-bye, and we'll be seeing each other soon. Okay, thank you.